X number 40, we have basking on the sun. So we've got a lizard basking on the sun. They're giving us a 15 degree with respect to the horizon, so I'm going to draw the horizontal. So we have 15 degrees. That's 15.0. 3 sig big. Dun, dun, dun. This is the lizard. The mass is equal to 9.10 kilograms. What is the magnitude of the force normal? So, force weight, which is equal to mass times gravity as always, which is 9.81 meters per second squared times 1.1. So I'm going to write it all out again. Newtons. All right, and force normal, remember, isn't going to be straight up. It's going to be at a slight angle, and in fact, it's going to be at a 15 degree angle off of. So this is 15 degrees. And that is the force normal that we're looking for. And that is what we're looking for. Alright, so there's also some other forces here that will not actually probably matter. So it's called a static friction if we're not moving. There will be a couple different ways to set it up, but there will be one that is the easiest. So what we essentially have to do is decide where do we want our X and Y axis. And there is no movement because he's laying there. So we know that that force is equal to the force weight in the Y, but let's change the layout. Okay, we're going to do our x-axis here. I think is probably going to be, probably been a little too much there. And here, assuming that that was actually at a 90 degree angle, but it was not a good job there. Shoot. Should we undo? All right, and then okay, so we know that obviously this is my X and Y axis, so that's going to be a right angle, and so is the one above. The reason I picked this was because if it was motion, that's the way it was going, and it puts the force normal on the axis, and we just have to resolve our known value rather than our unknown. And resolving a known value is much easier. So let's resolve our force weight onto the X and the Y axis. So we'll have okay. Let's shut my pencil off again on accident. Alright, let's resolve force weight in the Y and our force weight in the X. Okay, this is also going to be a 15-degree angle. And feel free to pull your angle down and look at it if you struggle with seeing that. What I mean is pull this down to here and then do your alternating interior angles and summation of angles for 90 degrees and you'll see it. Alright, force weight in the Y is going to be my adjacent and the force weight in the X is my opposite. So cosine of 15.0 degrees is equal to my adjacent, which is my force weight in the Y, over my hypotenuse, which is my force weight of 10.791 newtons. I'll solve here in a sec, but I want to write out my other one. So sine 15.0 degrees is equal to force weight in the X divided by 10.791 newtons. So that means that I get a force weight in the Y of cosine 15 times 10.791. I think you're going to hear my cat vomiting in a second. Fabulous. 10.4 newtons. We're going to do 3 sig figs here, so I have to write them all out. Force weight in the X is sine of 15 times 10.791. Hey, what's going on? Maybe the battery's dying on my pen here, I don't know. 2.79 newtons. Alright, so I have now resolved my force weight in the Y and my force weight in the X. So I'm going to take this guy and kind of flip him around just so you can see the X and Y axis. So I'm basically twisting this 15 degrees to the right. So we would have the force normal as an up. I just want you to be able to see how this is making sense here. So I'll do my Y forces in blue, and then you'll have your force weight in the Y acting down, which is 10.4 newtons down. Alright, and then in the Y, we're going to have the frictional force that is, keeping the lizard from going down. The static friction, and then we've got the force weight in the X, which is 2.79 newtons. Alright, so if these are all the forces acting on this object, and we know this, and we know this, it makes it pretty easy to find the other ones. And the reason being, remember, is Newton's second law. It states that the summation of the forces in the X is equal to mass times acceleration, and the summation of the forces in the Y is equal to mass times acceleration. The difference being its acceleration in the X and Y respectively. So, even though we know the mass of the lizard is irrelevant, we know that the acceleration for both of these is 0. Because it is not moving, there is no acceleration. So we're going to set this equal to 0, and we're going to set this equal to 0. So if we take and sum the forces in the X, we're going to have in the positive. Remember, we're looking at the pink in this diagram for the X, the horizontal. So we are going to have the frictional force in the positive direction, keeping this guy up, minus the force weight in the X, which equals 0. that tells us that we can figure out that one. And then the one that we were actually looking for this problem, which is the force normal, which is acting up, minus 10.4 newtons, which is the force weight in the y, is equal to 0. Tells me that my force normal should be 10.4 newtons. Because if we were to, again, just ignore this and just look at it as an algebraic solution, you are going to add force normal, or add 10.4 newtons to both sides, and you get that force normal is equal to 10.4 newtons, which is what you were looking for. Alright, so that was 40. Jumping into 41. I'm going to try to move quicker. Oh, 3-tiered birthday cake. Oh, good. This one's easy to move quicker. 1, 2, 3. Rests on a table from bottom to top. These are the weights. So you have 16 newtons, and you have 9 newtons, and you have 5 newtons. What is the magnitude and direction of normal force acting on the second tier? So the second tier, is right here. So we want to know what's the normal force acting on that guy. So force normal is what? Right there. So what you're going to need to know is what is force weight. Because this is a simple solution where the force weight is equal to the force normal because there is no motion. And because... Sorry, dogs. Ashley, go see what Sky's freaking out about, please. That those are the only forces in play there. So we are going to take 5 newtons plus 9 newtons, and you will have 14 newtons as your force weight. And if you were to sum the forces and set them equal to mass times acceleration, you would find that your force normal is also 14 newtons up. 42. A stagehand starts sliding a piece of stage scenery. Sky. Originally it rests by pulling it horizontally with a force of 176 newtons. Alright, draw a picture. Some stage thing is pushing it, no, pulling it horizontally. So they are pulling horizontally. So force pull equals 176 newtons. What is the coefficient of static friction between the stage floor and the 490 newton? Oh, that's big. Force weight equals. This is something you should have been able to figure out when they say that it is 490 newtons. That is the force weight. What we want to figure out is there's some sort of static friction. Remember, it's equal to force normal times, whoops, that's not times, that's equals, so, force normal. Okay. And let's read it again. Sliding it at rest, pulling it horizontally. What is the coefficient of static friction between the floor? We want to figure out. What is this? Oh, they said static. Okay, so what that means is at the point where the force pull is equal to the friction, because that is at the moment that you're overcoming it. So we're going to say then that this 176 newtons and this static frictional force are the same. And again, the reason we know that is they're saying what is the mu s. Okay, mu s is the static friction that we're looking at. So static friction is that point at which the frictional force is overcome by this force. So we set it equal. So we say if your static frictional force is equal to 176 newtons, we are going to set that equal to force normal times mu s. And we're going to solve for mu s, but we have to figure out what force normal is. And force normal is pretty easy to solve because force normal is going to be equal to the force weight because there is no other forces at play in that direction. Again, you can set it equal to that by doing Newton's second law and setting it equal to mass times acceleration, and there's no acceleration, set equal to 0. Alright, so 176 newtons is equal to force normal of 490 newtons times mu s divided by 490 divided by 490. We get mu s is equal to 176 divided by 490. So, how many is it big? Two siblings. There it is. Remember no unit for, when do we do that? No unit when you have a coefficient of static friction. Alright, sorry, I'm trying to save this and it's not more. So I'm going to have to open a new one because I ran out of pages. So I'm going to save this.